Good evening. Uh, this is a work done, if you're familiar with the Erasmus program, uh, Erasmus has expanded outside Europe with the international Erasmus. So last year, uh, this time, we hosted Mustafa Kara from University of El Kuwait in our laboratory in the Hellenic Mediterranean University, Department of Electrical and Computer Engineering. We have the Laboratory of Intelligent Systems and Computer Architecture. So this work was done there. At that time, Mostefa was a PhD candidate. Now he has received his PhD from the University of El Kuwait in Algeria. To Konstantinos Karampidis that he was supposed to be here and present it because it's Easter week. He went to Athens, so I'm presenting it here. Mostefa is in Algeria, and Muath AlShaikh is in Saudi Arabia. So this is part of the PhD studies of Mostefa Kara. So we'll have introduction, contributions, scheme properties, proposed crypto system, properties demonstration, cryptanalysis, experimental results, and conclusion. Excuse me, I need to put some notes. Okay, there are many efforts. There are many efforts to face various challenges in the fast-moving field of network security and data exchange. Efforts vary to address multiple issues such as computational speed, data size requirements, application scope that are driven by the purpose of collecting and sharing sensitive data that must be stored and processed securely. This paper proposes an efficient asymmetric crypto system where the plain text is encapsulated by a variable key with ensuring data integrity. So, this work has two main contributions, a public key crypto system and a vertical encryption. So we have the plain text encryption, clip text description. The principal properties of the proposed technique can be summarized as follows. It is asymmetric, probabilistic, additive homomorphic, and data integrity ensuring. So symmetric encryption employs a single secret key that requires to be shared between communications who need to exchange data. Therefore, anyone can decrypt the plain text by using the secret key. Asymmetric encryption employs two keys, eliminating the need to share keys. Anyone can access the public key, which is used to send, as we see, encrypted data. The private key is preserved as a secret, and only the owner can access it. Each message is encapsulated by utilizing the public key, can only be described with a private key. Therefore, symmetric approaches are less secure compared with asymmetric ones due to the use of single key. So probabilistic encryption is more secure because the data has been turned into random string. When a deterministic encapsulation approach is utilized, the enemy can just encrypt all guest messages by employing the known public key and then comparing the result with the target. If successful, he would be able to extract information about the private key. To avoid this situation, the technique must include a part of randomness, guaranteeing that the encapsulated message will be hidden in one of a large number of probable ciphertexts. Data are often encrypted by their owners before they are stored in the cloud. The problem is that the unreliable third party will need data into clear form to perform calculation on it, and this does not satisfy clients because it produces security threats affecting their privacy, requiring clients to decrypt cloud data, perform calculations on it, encrypt the results, and send them back to the cloud is not acceptable solution, as all homomorphic encryption can solve this problem by enabling a third party to perform operations on encrypted data without the need to decipher them before. So the data, let's assume that the user asks the cloud to perform homomorphic addition of two ciphertexts. Upon receiving the result, the user will use it on the basis that is valid computing. However, in reality, the third party may have changed this result, whether by mistake or on purpose. Clients cannot discover their erroneous result, especially in the cloud has done several excessive homomorphic operations on the data before sending it back to the client. Thanks to the proposed scheme, clients can verify the result's validity. The algorithm of the encrypted here. P and Q, we consider them very large prime numbers, and we use residue arithmetic. The sender that encrypts the message MI generates randomly RI for each MI and computes PK, the public key. And as we see, PI is PK0 to the MI modulo N, where N is P times Q. So the receiver does not know PK. He uses PK0, constant and known to everybody, to verify the integrity of the message M. After extracting C and extracting M, the receiver also computes key prime K and computes PK to see if it's the same as TI. This is the proposed crypto system description. Requires CI, PI, K, and P, ensures an I, and goes through all this process that I mentioned before, that we try to see if PI estimated is the same as TI, we return. These are some properties demonstrated in the description has to do with residue arithmetic and more properties demonstrated additive homomorphic, and this is all the operations that we prove the concept. They do keep the theta credited. CI is MI times PK1 mod N, and C2 M2 times PK mod 2, T1 PK0 to the M1, and T2 PK0 to M2. The additive operation computes C3 and T3 based on C1, C2, E1 and T2 respectively, which gives us T3 PK0 to the M plus 1 plus M2 mod N. The user describes C3 in the normal case, then he computes T estimated 3, and if T3 estimated is equal to 2, 3, the data integrity is assured. The present crypto system is based on two classes of robustness. The first part, C, is based on the factorization problem. The robustness of the second part depends on the discrete logarithm hardness. Our scheme resists the following attacks: brute force attacks, chosen plain text attack, and on plain text attack. The proposed method was compared with 5 other methods. In the following slide, the 5 other methods are described in these references, and the one that we proposed is the best. As a conclusion, due to the good features of probabilistic encryption, has it facing many types of attacks. This work presented a linear probabilistic encryption scheme. The proposal also ensures result integrity when an untrusted third party performs a homomorphic addition on encrypted data. Security analysis and performance comparisons are demonstrated. The experimental results showed its feasibility in low power environments. Thank you.